On October 14th, 2025, Windows 10 reached the end of support, and millions of working computers crossed an invisible corporate deadline. Their processors had not failed, their memory had not vanished, their screens still lit up, yet the machines had suddenly become unsupported. Microsoft presented 3 official paths: move to Windows 11, pay for extended security coverage, or replace hardware that failed its requirements. For many owners, the problem was not speed, it was eligibility. Windows 11 demanded a supported processor, TPM 2.0, and secure boot capability. A computer purchased, maintained, and physically owned by its user could still be pushed outside the supported future by a software policy. Nothing inside the case had broken that morning. What changed was the permission structure surrounding the machine and its operating system. That moment exposed a conflict modern computing hides. Buying hardware does not always mean controlling what the hardware is allowed to become. A laptop may belong to you legally, yet its supported life, identity requirements, updates, and data flows can remain shaped by a distant vendor. The silicon cage is not a locked metal box. It is a stack of dependencies that turns ownership into a carefully managed form of access. It begins in firmware, continues through the boot process, enters the operating system, and reaches cloud accounts attached to daily activity. Each layer may offer security or convenience. Together, however, they can move decisive control away from the person sitting at the keyboard. Windows 11, Home and Pro for personal use, require internet access and a Microsoft account during initial setup on officially supported installations. The system also sends required diagnostic information about devices, configurations, quality, compatibility, and parts of the Microsoft Store. Optional settings can expand collection into areas such as browsing activity, software inventory, and typing, speech, or inking interactions. None of this proves that every Windows machine is secretly recording every action. The reality is less cinematic but structurally important. The operating system is no longer only a tool executing local commands. It is also a managed service connected to an external commercial platform. Updates arrive according to a life cycle the vendor defines. Features can be added, retired, promoted, delayed, or tied to online services. The user can adjust many settings, but the boundaries of those settings are still designed by the company maintaining the proprietary code. Then a different possibility appears. Erase the vendor-controlled operating system and install one whose source can be inspected and changed. Linux does not make the processor faster by ideology. It changes the authority governing the machine and the choices available to its owner. On the same hardware declared too old for one supported path, Linux can often install, update, and operate without demanding a new computer. That supported path is where the argument becomes more complicated. Microsoft did not invent hardware security merely to inconvenience users. TPM 2.0 can protect encryption keys, secure boot can block unauthorized bootloaders, and automatic patches can close vulnerabilities before ordinary owners understand the danger. The cage is built partly from protections people genuinely need. Protection becomes control when the protected person cannot meaningfully refuse its terms. In practice today, the problem is not that these mechanisms exist. The problem is who controls their defaults, exceptions, life cycles, and acceptable uses. A security feature can defend the owner, defend the platform, or do both at once. When the implementation is closed, the user must trust the vendor's explanation of where those interests separate. The question is whether security remains subordinate to informed owner consent. Proprietary software asks for trust at every critical layer. The executable arrives without the complete human-readable source used to build it. Independent researchers can inspect behavior from the outside, but ordinary users cannot audit the entire decision-making process. They receive a finished product, a license, and a set of settings permitted by its designer. Linux changes this arrangement because the kernel is distributed under the GNU General Public License version 2. Its source is available, modifications can be studied, and redistributed versions must preserve key freedoms. No single desktop company possesses the exclusive legal power to decide what every Linux computer may run or how long it remains useful. That legal architecture turns inspection and modification into durable rights, not favors. That does not mean every Linux user reads kernel code. Most never will. The practical protection comes from the possibility of inspection. Universities, security teams, distribution maintainers, hardware vendors, and independent developers can examine the same foundations. A suspicious change cannot depend forever on the assumption that nobody outside one corporation will see it. This distributed scrutiny is not perfection. Open code can contain serious vulnerabilities for years. Maintainers can make mistakes, projects can lose funding, fragment, or disappear. But the failure remains technically visible, and another group can continue the work. The system's survival is not inseparable from one company's product strategy or quarterly priorities. The word Linux also hides an important choice. Linux is the kernel, not one single consumer operating system. Ubuntu, Fedora, Debian, Linux Mint, OpenSUSE, Arch, and many other distributions, Combine that kernel with different installers, update policies, desktops, repositories, and philosophies. Escaping one gatekeeper does not require accepting another universal gatekeeper. A beginner can choose Linux Mint for a familiar desktop, Ubuntu for broad commercial support, Fedora for newer technologies, or Debian for conservative stability. A specialist can choose an atomic desktop, a minimal installation, or a distribution assembled almost entirely by hand. The machine can serve the owner's priorities instead of a universal marketing profile. Choice becomes practical when each option reflects a different operating philosophy. The first act of reclamation should not be installation. It should be an audit. Every essential application, peripheral, file format, cloud dependency, and security requirement must be listed before the existing system is erased. Sovereignty achieved by destroying irreplaceable work is not sovereignty. It is simply an avoidable failure wearing ideological clothing. The audit usually reveals 3 categories. Some tasks already have native Linux software. Others can move to web applications or cross-platform tools. A final group depends on Windows-only programs, proprietary drivers, specialized plugins, or corporate policies. The migration succeeds when these categories are identified honestly rather than buried beneath enthusiasm. But names alone do not guarantee equivalence. Complex Microsoft Office documents can change formatting. Adobe workflows may depend on applications without native Linux versions. Professional audio hardware can require vendor control panels. Accounting systems, engineering suites, and organization-specific security agents may refuse to run. The cost of freedom must be measured before it is paid. This is why a live USB is so powerful. It allows Linux to boot without immediately replacing the installed operating system. The user can test Wi-Fi, Bluetooth, audio, graphics, sleep, external displays, touchpads, cameras, printers, and storage. The first battle for hardware control is won by gathering evidence, not by assuming compatibility. Testing before installation converts ideology into measurable evidence about the actual machine. Canonical certification program tests selected systems across hundreds of hardware functions, and major manufacturers sell machines validated for Ubuntu. Yet millions of uncertified computers also work well because drivers for common hardware are included in the kernel. Linux often recognizes a device during installation without searching a manufacturer's website for a separate package. Compatibility is strongest when hardware vendors cooperate upstream. A driver merged into the mainline kernel can travel through distributions and remain maintained as the kernel evolves. A closed external driver creates a weaker dependency. It may break after an update, lag behind new kernels, or disappear when its manufacturer loses commercial interest. This is one place where the silicon cage survives beneath Linux. Many Wi-Fi adapters, graphics cards, audio processors, fingerprint readers, and embedded controllers require proprietary firmware. The Linux kernel may provide an open driver while still loading a binary blob whose internal code the user cannot inspect. Installing Linux does not magically open sealed silicon. Modern processors also contain management engines, microcode, security processors, and firmware below the operating system. A Linux installation sits above those layers. It can reduce dependence on a proprietary desktop platform, but it cannot transform undocumented hardware into completely user-controlled machinery. Digital sovereignty is a direction, not a magical state, achieved after one reboot. Linux cannot audit what the processor itself refuses to reveal completely. That realism makes the next decision more important, whether to dual boot or replace Windows entirely. Dual boot preserves access to incompatible applications, while Linux becomes the daily environment. It lowers risk, but it also keeps both systems competing for disk space, boot configuration, attention, and the user's habit of retreating whenever friction appears. A clean replacement creates a sharper break. The drive is repartitioned, a Linux file system is created, and the former operating system disappears. Before that moment, backups must be tested, recovery keys exported, browser data synchronized or copied, and encrypted files verified. A backup that has never been restored is only a theory. Full disk encryption should be considered during installation, not after a laptop is lost. Linux installers can create encrypted storage using established tools such as LUKS. The protection is meaningful only with a strong passphrase, secure backups, and an understanding that encryption defends data at rest, not a compromised session after login. Then comes identity. Most Linux distributions allow a local account by default. The username and password authenticate against the machine itself. Cloud accounts can still be added for email, calendars, file synchronization, or browsers, but they are services attached by choice rather than mandatory identities required to reach the desktop. Telemetry also becomes a question rather than a permanent background assumption. Some Linux distributions collect limited technical metrics, crash reports, or installation statistics, often with documented settings. Others collect almost nothing by default. Because the ecosystem contains alternatives, a user who rejects one policy can change distributions without abandoning the Linux kernel. Competition gives privacy policies consequences that closed ecosystems often avoid entirely. Open source does not guarantee privacy from every application. A proprietary browser, chat client, game launcher, or cloud storage tool can collect data on Linux just as it can elsewhere. Moving operating systems while reinstalling the same surveillance-heavy services may change less than expected. Sovereignty requires examining the entire software stack, not worshiping the kernel. The strongest privacy improvement often comes from reduction. Fewer background launchers, fewer accounts, fewer browser extensions, fewer applications with unrestricted access to home folders, microphones, cameras, and networks. Linux makes this reduction possible, but the owner must still choose it. Freedom unused can resemble the system it replaced. Application packaging adds another layer of control. Traditional Linux repositories distribute software reviewed and integrated by maintainers. Flatpak packages can run inside sandboxes where access to files, devices, and services is explicitly granted. Portals allow an application to request selected files without automatically seeing the entire home directory. Updates reveal the deepest contrast. On Windows, the user can schedule, pause, and configure parts of the process, while Microsoft defines supported versions and eventually enforces lifecycle boundaries. On Linux, policies differ. Some distributions notify and wait, others update automatically. Rolling releases expect frequent maintenance. Atomic desktops download a new system image and switch on reboot. Fedora's Atomic desktops, including Silverblue and Kinoite, can apply operating system updates as a new deployment and roll back to the previous version when necessary. This does not eliminate risk, but it changes failure recovery. An update becomes a reversible system state rather than an uncontrolled pile of replaced files. Traditional distributions provide another kind of power. The user can inspect proposed package changes, decide when to install them, hold specific packages, select kernels, and choose repositories. That flexibility can preserve a production workflow, but delaying security fixes indefinitely creates its own danger. Control does not mean rejecting updates. It means governing them intelligently. The administrator gains timing authority without pretending delayed patches are harmless. The sovereign approach separates urgency from interruption. Security patches can be installed quickly. Major release upgrades can be tested, and reboots can happen when work permits. Snapshots allow rollback. A second kernel can remain available in the boot menu. The user designs a maintenance policy suited to the machine rather than inheriting one universal consumer schedule. That freedom can also overwhelm. A command copied blindly from a form can damage permissions, remove packages, or weaken security. Root access is absolute because the system assumes the administrator understands the consequences. Linux removes protective corporate boundaries, but it cannot remove physics, mistakes, or the need to learn. The terminal is often presented as either a symbol of liberation or proof that Linux is unfinished. Both views are exaggerated. Modern desktops can handle ordinary work graphically. The terminal matters because it exposes automation in composition. A repeated task can become a script can become a service, and the workstation can adapt to its owner. This is where Linux begins to change the economics of hardware. A lightweight desktop can keep an older processor useful. Unnecessary startup services can be removed. Storage can be repurposed for local backups, media libraries, development environments, or self-hosted applications. The machine is no longer evaluated only by whether it qualifies for the newest commercial interface. Consider a functional laptop whose processor is outside an approved Windows list but still handles browsing, writing, and video playback. Under one lifecycle, it becomes a replacement candidate. Under Linux, it can receive a current kernel, security patches, a modern browser, and years of additional service depending on distribution support and hardware condition. The environmental consequence is real even when it is difficult to quantify for one device. Extending hardware life delays manufacturing, shipping, and disposal. Linux cannot repair a dead battery or inefficient processor, and sometimes newer equipment genuinely saves energy. But software policy should not be confused with physical failure. Reclaimed hardware can also become specialized infrastructure. An old desktop can serve encrypted backups. A mini PC can host a local media library, password manager, website, development environment, or home automation controller. A laptop can become an offline writing station. Linux allows roles that do not depend on a vendor's preferred consumer upgrade path. Local infrastructure does not automatically become secure. A self-hosted service exposed carelessly to the internet can be more dangerous than a professionally managed cloud account. Ports, certificates, authentication, backups, updates, and access logs require attention. Sovereignty transfers responsibility inward. It does not make threats disappear. Gaming once represented one of the strongest reasons not to leave Windows. That barrier has weakened because Valve's Proton translates Windows game interfaces through Wine and related components. Thousands of titles can run without native Linux versions, and the source is available for inspection and modification. But compatibility remains a title-by-title reality. Some games still fail because of unsupported anti-cheat systems, media codecs, launchers, or developer decisions. Valve's own documentation requires developers to configure certain anti-cheat support for Proton. A player whose social life centers on one incompatible competitive game may rationally keep Windows, dual boot, or delay migration. The same honesty applies to creative work. Linux is exceptional for software development, servers, 3D creation, and many media workflows. It can be frustrating when a client demands a proprietary format or plugin available only on another platform. Reclaiming control does not require pretending alternatives are identical. It requires choosing where dependence is acceptable. A migration plan should preserve paid work before pursuing ideological completeness. Virtual machines provide one compromise. A Windows guest can run inside a Linux host for applications that do not need direct access to specialized hardware. The proprietary environment becomes contained rather than dominant. Its network can be limited, snapshots can preserve state, and the main files can remain under the host's control. Secure Boot demonstrates the same transformation. It is not inherently an enemy of Linux. Major distributions provide signed bootloaders and can operate with Secure Boot enabled. The security benefit is real when the owner controls trusted keys and boot policy. It becomes restrictive only when hardware prevents the owner from authorizing another legitimate system. Some computers make alternative booting difficult through hidden settings, locked bootloaders, unsupported storage controllers, or firmware designed almost exclusively around one operating system. Research before purchase therefore matters more than any later command. The most sovereign Linux workstation begins with hardware, selected for documented compatibility, repairability, and replaceable components. Buying decisions are votes cast years in advance. A laptop with soldered storage, inaccessible firmware, and unsupported peripherals can limit freedom regardless of operating system. A machine with standard components, upstream Linux support, replaceable storage, and published service documentation creates options that survive after the original warranty ends. This is why Linux migration should not be framed only as a protest against Microsoft or Apple. The deeper objective is resilient computing. A resilient workstation can function locally, recover from failure, change software suppliers, preserve standard file formats, and continue operating when a cloud service, product line, or corporate policy changes. File formats become part of sovereignty. Plain text, open document standards, common image formats, and widely supported archives reduce dependency on one application. Proprietary formats may be unavoidable, but they should not become the only copy of valuable work. The ability to open a file 10 years later matters more than the animation surrounding it today. Cloud storage deserves the same treatment. Synchronization is useful, but synchronization is not backup, and access is not ownership. A provider can change pricing, limits, authentication, or features. Linux makes local storage and self-hosting natural, yet the strongest design often combines encrypted local copies with carefully selected remote backups. The workstation can then be rebuilt from documented pieces. A package list records applications. Configuration files live in version control. Containers isolate services. Automated jobs create backups and verify them. Installation media remains available. If the disk fails, the owner restores a system rather than reconstructing a corporate account relationship. Containers are not magical walls, but they reinforce the idea that applications should receive only the resources they require. A service can run with limited file system access, restricted capabilities, and a controlled network. The owner defines the boundary. This is the opposite of installing an opaque package and hoping its background processes remain polite. The right to leave may be the most important right in technology. A platform behaves differently when users can export data, replace components, install another operating system, and continue working. Exit creates accountability. Without exit, convenience can slowly become dependence, and dependence can become a business model disguised as inevitability. Corporate control rarely arrives as one dramatic lock. It arrives as defaults. A required account here, a cloud backup prompt there, a feature that returns after an update, a file opened by an online service, a device excluded from support. Each decision can be defended individually, while their combined direction remains difficult to reverse. Linux reverses that direction through hundreds of smaller decisions. Create a local account, choose the file system, select the desktop, approve repositories, schedule updates, inspect services, remove unwanted software, encrypt the drive, keep data local. Every choice returns a fragment of authority to the person who purchased the machine. But control should never become paranoia. Network services are not automatically hostile. Telemetry can identify crashes and hardware problems. Automatic updates protect users who would otherwise remain exposed. Cloud collaboration can be transformative. The objective is not isolation from every company. It is informed consent, meaningful alternatives, and the ability to say no. Consent matters only when refusal does not destroy ordinary functionality immediately. A healthy Linux migration may still use Google Docs, Microsoft 365 in a browser, Steam, Dropbox, proprietary graphics drivers, or commercial support. Purity is not the test. The test is whether one service can hold the entire workstation hostage. Dependencies should be visible, limited, replaceable, and proportionate to the value they provide. The transition is complete when Linux stops feeling like an escape vehicle and becomes ordinary infrastructure. The owner turns on the computer, performs work, installs updates, and shuts it down without negotiating with the operating system. The absence of friction becomes more significant than the presence of a different logo. That ordinary experience is supported by an extraordinary global system. Kernel maintainers, distribution teams, translators, security researchers, desktop developers, and hardware engineers coordinate in public. Companies contribute because their servers, clouds, devices, and products depend on Linux. Volunteers contribute because the system's future is not reserved for shareholders. Corporate participation does not invalidate Linux freedom. It creates tension that open governance must continually manage. Large companies influence development, maintain critical components, and pursue their own interests. The protection is structural. Code can be reviewed, branches can be forked, and distributions can reject decisions that conflict with their users. This structure has already made Linux the foundation of servers, supercomputers, networking equipment, embedded devices, and much of the cloud. The irony is unavoidable. Many corporations rely on Linux internally while consumers remain told that personal computing must revolve around closed platforms, mandatory identities, and hardware replacement cycles. The desktop is where that contradiction becomes personal. A server administrator would never accept a production machine that changed critical behavior without testing, stored its only data copy in an uncontrolled account, or could not be rebuilt from documentation. Consumers are expected to accept versions of those risks in exchange for convenience. Reclaiming the workstation means applying infrastructure discipline to personal computing without turning daily life into a data center. Updates should be predictable. Backups should be automatic. Recovery should be tested. Applications should be replaceable. Accounts should be optional where possible. The machine should continue performing essential tasks when the internet is unavailable. This future does not require every person to become a kernel engineer. It requires tools that convert technical freedom into usable defaults. Friendly installers, hardware certification, graphical permission controls, atomic rollbacks, reliable app stores, and accessible documentation are not compromises with freedom. They are how freedom reaches people who cannot maintain everything manually. The greatest threat to Linux adoption is therefore not complexity alone. It is the belief that inconvenience proves authenticity. A sovereign workstation should be easier to recover, easier to understand, and easier to keep for years. Freedom that requires constant suffering will remain a niche, while polished dependence continues winning by default. By the time a user reaches this point, the original computer has changed without changing physically. The same processor executes instructions. The same memory stores active work. The same display illuminates pixels. What has changed is the chain of authority connecting those components to decisions made outside the room. Yet the final victory is not deleting Windows. It is building a system that can survive the next dependency. A careless Linux installation tied entirely to one cloud, one proprietary application, or one undocumented device can become another cage. The bars may be rearranged, but the structure remains. True hardware reclamation combines open software with repairable devices, portable data, tested backups, limited permissions, and the confidence to migrate again. Linux is powerful because it makes that architecture possible. Its greatest promise is not loyalty to Linux, it is freedom from permanent loyalty to any platform. The October 2025 deadline revealed that modern computers can become commercially obsolete while remaining physically capable. Linux answers by separating usefulness from a vendor's calendar. It allows the machine to keep serving its owner, but only if the owner is willing to trade passive convenience for deliberate control. That trade is not a retreat into the past. It points toward a more durable future. Local-first workstations, connected to services by choice, systems that can be audited and rebuilt, applications contained by permissions, and hardware kept alive until its physical limits, not a marketing deadline, finally end its service. The silicon cage was never made from silicon alone. It was made from accounts, licenses, opaque code, remote policies, incompatible formats, and the assumption that ordinary users should not control the machines they purchased. Linux does not shatter every bar, but it gives the owner tools to see them. And once those bars become visible, the meaning of ownership changes. The computer is no longer a terminal rented from a corporate ecosystem. It becomes a workstation whose rules can be questioned, whose failures can be investigated, whose data can remain local, and whose future can be chosen. The escape is not completed by the installation screen. It is completed each time the machine obeys its owner rather than a business model, each time useful hardware survives an artificial deadline, and each time a dependency becomes a choice instead of a command. That is the real promise of Linux. Not a perfect operating system, not a world without companies, and not freedom without responsibility, but the return of a simple principle: modern computing nearly erased. The hardware you bought should answer to you.